The atmosphere of Earth, the probability of storm can be predicted, but nothing can be done to stop or slow a storm, can it be? Yes, maybe it may be possible in near future. Understanding the atmosphere may help in predicting weather changes, but it is doubtful that weather will ever be controlled on a large scale. But I wish we could. So we'll see about the atmosphere. Our main agenda is knowing the atmosphere. The composition of atmosphere is like this: nitrogen, that is N2, is the most abundant gas in the Earth atmosphere, which is making up to 78%. Oxygen is the second most abundant, how we live, making up about 21%. And nitrogen cycles in the atmosphere through the nitrogen cycle as it is removed from the atmosphere by bacteria and lightning. Nitrogen. So these nitrogen compounds are then taken up by the plants and utilized for the growth and development. Oxygen also cycles in the atmosphere. Living organisms are used they as food sources. They use it as food sources, and oxygen is utilized in most organisms that digest other organisms. Chemical weathering of rocks can cause oxides to form, locking up the oxygen within the minerals. And oxygen is released into the atmosphere by plants as they photosynthesize. Water. Water in the atmosphere varies considerably and also cycles in the hydrologic cycle. This is the cycle of evaporation and condensation that results almost daily. Then carbon dioxide. It makes up approximately 0.03% of the Earth atmospheric gases. Carbon dioxide concentration in the atmosphere is regulated by first removal of CO2 from the atmosphere as green plant fix the CO2 into carbohydrates. Then exchanges of CO2 between atmosphere and the oceans, and chemical reactions between the atmosphere and the limestone. This is the overall concentration. Earth atmosphere has a unique composition of gases when compared to that of other planets in the solar system. So oxygen 21% mostly, nitrogen we have, and all others consisting of 0.03% argon about 1%. Atmospheric pressure. What it is? The atmosphere exerts pressure on the earth that decreases with increasing altitude. That means if this is earth, we have more pressure here than at certain more distance above. This is due to the fact that the with increasing altitude, there is a decrease in the column of gases about the earth's surface. Hydrostatics considers the pressure P that is exerted by a fluid that is at rest. Using this as a frame of reference, the atmospheric pressure is viewed as the result of the mass of the column of gases which are above Earth. Using a molecular frame of reference, the atmospheric pressure is viewed as a result of the kinetic energy of the molecules and the force with which they strike an object. Atmospheric pressure is actually a result of the interaction between these two factors. At greater altitudes, the same volume contains fewer molecules of the gases that make up the air like this. This means that the density of air decreases with the increasing altitude. The increase in the altitude. Here we have dense molecules and here we have sparse. The Earth atmosphere thins rapidly with increasing altitude and is much closer to the Earth than most people realize. So this is depending upon the distance. If it is a 5.6 kilometer, we have about 50% of mass, 32 about 99% of mass. The mercury barometer measures the atmospheric pressure from the balance between the pressure exerted by the weight of the mercury in a tube and the pressure which is the by the weight of the mercury and the pressure exerted by the atmosphere. As you see here, this is the atmospheric pressure. So as atmospheric pressure increases and decreases, the mercury it rises or falls. So this is what we see in this figure. It shows the average height of the column at the sea level. Warming the atmosphere, because how we can warm the atmosphere, how the atmosphere warms itself. So the temperature of an object is actually a measure of kinetic energy of the molecule that makes up the object. And any object that contains any kinetic energy at all, that is, it has a temperature above, say, absolute 0 Kelvin, gives off radiant energy. Solar constant. When the sunlight is perpendicular to the outer edge and the earth is at average distance from the sun, it produces 1370 watts per meter square. This quantity is believed to remain constant. This is solar constant. So on an average, the Earth's surface absorbs only 51% of the incoming solar radiations. After it is filtered, absorbed and reflected, this does not include the radiation emitted back to the surface from the greenhouse effect, which is equivalent to 93 units of the percentages in this figure. So we have various, if this is the 100% incoming solar radiation, 6% is scattered by the air, 20% is reflected by the clouds, 3% absorbed by the clouds, 16% by the air, and 4% reflected by the surface, Earth surface, and 51% is absorbed by the surface, Earth surface. So structure of the atmosphere, we have observed lab state, that is the temperature decreases approximately 6.5% of degree centigrade for each kilometer, per kilometer of altitude. Inversion means when a layer of the atmosphere increases, when a layer of the atmosphere increases with altitude. What about troposphere? The layer of the atmosphere from the surface of the earth up to where it stops decreasing in temperature, up to height of about 11 kilometer. Somewhere it is more than that, because earth is not completely complete circle or sphere. So at equatorial ranges it will be different, and on the poles it may be different. But on an all average it is 11 kilometers from the earth's surface. Air is constantly mixed due to denser air being above. So then we come to the tropopause. Tropopause. The upper boundary of the troposphere, the temperature remains constant with increasing altitude. Then stratosphere, temperature begins to increase with height. Very stable as denser air is below less denser air, which is up to 48 kilometer. So 0 to 11, then 11 to 48 kilometer. Temperature increases as a result of interaction between UV, that is high energy ultraviolet radiation, and ozone, that is O3. Then we have stratosphere, where the temperature reaches a maximum of 10 degree. Ozone shield, that is 50 degree Fahrenheit. Then we have ozone shield, a layer of ozone that absorbs much of the UV radiation that enters the atmosphere. It provides a significant shield to the earth below from damaging UV radiation. Then we have mesosphere. Temperature again begin to decrease due to the decrease in the gas molecules to absorb radiation. And then we come to thermosphere. Temperature again begins to rise due to the presence of molecular fragments which absorb radiation from space. Temperature is extremely high here due to the average kinetic energy of the molecules, thermosphere, and very little energy transfers. However, due to the lack of molecules, very few molecules to collide with the objects. Then the exosphere, outermost layer of the atmosphere, where molecules merge with the vacuum of space. The high kinetic energy of the molecules at this height are significant enough to cause them to be able to escape into the space. Then we have ionosphere, alternative name for the thermosphere, and upper mesosphere. Due to the occurrence of free electrons and ions, they are ionosphere. It is the electrons and the ions in this layer that cause radio waves to be able to be reflected around the world, ionosphere. So this is the structure of the atmosphere based on the temperature differences. And we need to know the pauses, the stratopause, the mesopause, the tropopause. These are actually not lines but are broad regions that merge. So this is the altitude with the temperature variation. Then the winds. Local wind patterns. These are due to the relationship between your air temperature and air density, the relationship between air pressure and the movement of the air, and the upward and downward movement of air which leads to the upward movement has a lifting effect on the surface that creates areas of low pressure, and the downward movement, this one of the air, has a piling up effect resulting in the areas of high pressure. So this is the model of the relationship between differential heating, the movement of air and the pressure difference in a convective cell. Cool air pushes the less dense warm up air upwards, reducing the surface pressure. So as the uplifted air cools and becomes more dense, it sinks, increasing the surface pressure. This is the convective movement of air. If you have high pressure, low pressure goes up, high pressure goes down. This is a cool surface, this is a warm surface. So adjacent area on the surface of the earth can have very different temperatures due to difference in heating and cooling rates. And this difference is usually greatest between bodies of water and adjacent land masses due to water has a high specific heat. Water is easily mixed, which keeps water cooler than adjacent land masses. And water cools by evaporation, which also keeps a body of water at a lower temperature. And this results in a sea breeze, since the denser, cooler air from the body of the water will move in under the less dense air over the land. Here, the land warms and cools more rapidly than an adjacent large body of water. During the day, the land is warmer and the air over the land expands and is buoyed up by cooler, more dense air from over the water. So, this is like this. And during the night, the land cools more rapidly than the water, and the direction of the breeze is reversed. Incoming solar radiation falls more directly on the side of a mountain, which results in differential heating. The same amount of sunlight falls on the areas, we show this in the illustration, with the valley floor receiving a more spread out distribution of energy per unit area. The overall result is an upslope distribution of energy per unit area. So the overall result is an upslope mountain breeze during the day, and during the night, dense cool air flows downslope for a reverse wind pattern. Global wind patterns. Hot air rises over the equator due to the fact that it is less dense, and this is called the intertropical convergence zone. So this rising air cools adiabatically as it rises, resulting in the high precipitation. So the cooled air descends to reach the surface at about 30 degree north and 30 degrees south of the equator. This forms a high pressure area. The great deserts of the world are located at this high pressure area. Towards the pole from this pressure area, atmospheric circulation is controlled by a powerful belt of wind near the top of the troposphere, which is called as the jet stream. The jet stream is a loop of winds that extends all the way around the globe. It generally moves from west in both hemispheres, and warm air masses move towards the poles ahead of this trough, and cool air masses move towards the equator behind this trough. So on a global yearly basis, the equatorial region of the earth receives more direct sunlight or solar radiation than the higher latitudes. This gets higher solar radiation. As a result, average temperatures are higher in the equatorial region, more direct sunlight, and decrease with the latitude towards both the poles. This sets the stage for worldwide pattern of prevailing winds, high and low areas of atmospheric pressure, and the climate patterns. And parts of the generalized global circulation pattern of the Earth's atmosphere is shown here. The scale of the upward movement of the air above the intertropical convergence zone is exaggerated, just for clarity, and the troposphere over the equator is thicker than elsewhere, reaching a height of about 20 km. Water in the atmosphere. Water exists in three states on the earth: liquid when the temperature is above 0 degree centigrade, solid when the temperature is 0 degree below, and a gas when the temperature is above 100 degrees centigrade. So evaporation and condensation, we have humidity. The amount of water vapor in the air is the humidity, and absolute humidity is the measure of the amount of water vapor present at a given time. And relative humidity is the measure of the amount of water vapor present in the air relative to the amount that the air could hold at that temperature. So the maximum amount of water vapor that can be in the air at different temperatures, the amount of water vapor in the air at a particular temperature is called the absolute humidity. This is the absolute humidity with respect to the temperature. As temperature increases, the absolute humidity increases. The rate of evaporation depends on what? Surface area of the exposed liquid. Air and water temperature, the relative humidity, the rate of condensation, it depends on relative humidity and the kinetic energy of the gas molecules in the air. So this is the evaporation and condensation, they are occurring all at the same time. So if the number of molecules leaving the liquid state exceeds the number of returning, the water is evaporating. If the number of molecules returning to the liquid state exceeds the number of leaving, the water is condensing. And if the both rates are equal, the air is saturated. That is, the relative humidity is actually 100%. Dew point temperature, the temperature at which the relative humidity and the absolute humidity are the same, that is saturated air, we call it as a dew point temperature. Dew begins to accumulate on surfaces, forms on sea nights, that is, we have clear, calm, cool. These are we have fans like this are used to mix the warmer upper layer of air with the cooling air in the orchard on nights when the frost is likely to form. Condensation nuclei. What is this condensation nuclei? It gives condensing moisture in the atmosphere, something to condense on, and this is necessary for the production of moisture in the atmosphere, that is rain and snow. So as condensation continues, eventually there will be a point where enough water molecules have condensed on the nuclei that it can no longer remain airborne. It will then fall in the form of rain or snow. This figure compares the size of the condensation nuclei to the size of typical condensation droplets. And you note that 1 micron is 1 by 1,000th of a millimeter. So this is 0.2 micron. This is drizzle point, which is 300 micron. Fog and clouds. Both of these are water droplets which have been condensed from the atmosphere. An upward movement of air keeps them from falling, and clouds are identified according to whether they are cirrus, that is curly, cumulus, that is piled up, and stratus, that is spread out. An early morning aerial view of a fog between mountain at top and river below that developed close to the ground in cool moist air on a clear calm night. And in this figure we have fog which forms over the ocean where air moves from warm current over a cool current and the fog often moves. Thank you so much. This was all about the Earth atmosphere.